Hello, everyone. Welcome. We are really excited for our next session with Jose Quenum and Marthin Thomas. Really excited to learn more about the hybrid recommender system in Julia. Just a reminder to everyone, we'd love to have audience interaction, so please feel free to put your questions and comments in the chat. And we've just got some great information coming our way. So I'm going to go ahead and turn it over to Jose. Jose, thank you so much for being here today, and we'll turn it over to you.
Thank you very much. Thank you, Erin, and greetings, everyone. Good afternoon, morning, wherever you are. So I'd like to discuss our implementation of a hybrid recommender system, particularly the implementation we did in Julia for an HPC environment. First of all, let me give you some background. Typically, when you're developing a recommender system, you actually need three essential components, right? The first one is the candidate generation. And for the candidate generation, you can use two possible techniques, either content-based filtering, where you actually look for the similarities between the items, and based on the previous preference of the user, of the specific user you're targeting for items, right? You can just do a dot product and find the similarity, and based on that, recommend new items for the user. The other approach, common approach, is actually collaborative filtering, where you look at the similarity between other users and items, and then recommend an item based on what other similar users have actually recommended. And one way to do it is actually to use a weighted matrix factorization, which I summarized here. So the idea is to learn actually two latent matrices, the user representation and the item representation, and try and get a multiplication of those two matrices that is as close as possible to the interaction data that you've collected. And you can do it by taking into consideration data. If you have a sparse matrix, then you can take into consideration data that has been observed and the data that hasn't been observed. Then the next step is for you to score the items that the candidates that you generated. You can then do a scoring and then rank them first. And again, use additional criteria like freshness, diversity, and fairness to rank them, to give a chance to new items actually be recommended, or make diversity or fairness prevail in your recommendation. In our case, our focus was to actually develop a recommender system for candidate pre-selection in a recruitment process. And so we have two essential components, the job adverts that we've collected and the different applicant profiles. And so what we do is actually use some NLP techniques to extract the maximum information that we can from those two pieces of data, and then construct a heterogeneous graph. And in our heterogeneous graph, what we essentially represent includes the different job applicants and the job adverts. And so we will integrate the representation of the job adverts and the applicant, and we'll also the link in the graph, actually the edge, will indicate the score of the applicant, show how strong is the connection between a particular applicant and the job advert. Overall, this is the architecture that we adopted. So we take our initial data, a bunch of job adverts and applicants, and then we construct, so we extract the necessary information and construct a heterogeneous graph. And then we pass that heterogeneous graph to a graph neural network, where we, in fact, run several convolutional layers for representation. And once we understand the link between the between the applicant and the job advert. Then we pass it to a dense layer before we push the information to a transformer to further determine the score that we should allocate to for an applicant to a job advert. And that's how we eventually get the recommendation. I'll just keep. So the convolutional layers that we considered here, actually, there are 4 convolutional layers that we considered in this implementation. We have GCN, we have the Graph Attention Network, we have GraphSage, and RGGC. And what we do is actually train different models where we combine these different. So we'll run models where we have those layers individually, but we'll also run other models where we have a combination of these layers to further learn and then compare the quality of the recommendation. So this is the typical operation that happens during the convolution. The graph neural network, when it's doing the convolution, it does 2 essential operations: the update of the information after aggregating information from the neighbor. So it will take a node, and then from that node, look for aggregate information from the neighboring nodes, and then update its own the current node. So let's dive into the implementation based on the background that I just gave you. So our implementation uses a lot of predefined packages, flux, transformers, distributed, and so forth. And so we also, because of the, you can see that our architecture is quite heavy, so it requires a lot of compute resources. So we turn to an HPC environment, and the typical HPC environment that we use is a 48 node cluster, right, where each node has 24 cores CPU. Also, the network, the interconnect between the compute nodes is actually InfiniBand, a low latency InfiniBand interconnect. So basically, to submit a job in our environment, all you do is just prepare a script, right? And we're actually using the environment, HPC environment, we're using Slum. So all we do is just write a bash script that is actually compatible with Slum. And what we essentially provide in the script is just some a description of the resources that we require, right? How many nodes do we want for our computation? How many tasks are we executing, and how many tasks per CPU? Essentially, we load the Julia package and then run the Julia file. Here, I used one example where we have a file called model.julia, and that's what we'll eventually run. So we execute that script by simply calling the sbatch command and pass the path, pass the name of the script that I just wrote on the left-hand side. Before we start training the recommender system model, first we do our data preprocessing. And we do our data preprocessing in 2 stages. Right? The first stage is actually to collect the raw data and then transform them into data frames. So for that, first we have our applicants that are actually represented as a CSV file. And so we load them and then just sort the different applicant and create a data frame out of it. Very straightforward. And once we do that, we save it in a binary format. The next thing we do is actually load the job adverts, and that one requires. So here the setup is that we get the job advert as a bunch of text files in a folder. So we just provide the name to the folder and then extract each file. And once we extract the files, then we build a dictionary where we map the name of the file, right? Which in the naming, we have the job ID, the advert ID actually, and then the content that is provided in the text. And once we do that, then we create a new data frame. And the interesting thing is now we have two data frames, right? One that corresponds to the applicant, the other one that corresponds to the advert. And eventually we bring both of them together by doing a join where the common column is the job ID. So we make sure that on both sides we have the job ID column, and then we simply do a join and merge the two data, the two pieces of data. And then we proceed with generating the embeddings because there's a lot of textual information that we've extracted. And so we simply use word2vec here to extract the embedding vectors corresponding to the adverts themselves and the applicant profiles. The second stage of our data preprocessing is where we now embrace mostly distributed environment, where first of all we load all the packages that we need. So first of all, we require a number of processes from the Slum Manager, and then we load all the packages that we need on all the nodes that have been allocated for our job. And then one by one, first we load the applicants. Remember, once we did the first pre-processing of the applicants, we saved it in a file. So now we can just reload that file in all the nodes. Also, the embeddings, which is the kind of using the word2vec package, we were able to generate specific description for the applicant. So we also load the embeddings of the applicant. And finally, for the job advert, we also load the embedding vector. So we have three embeddings, right? The applicants, we have two embeddings and the binary representation of the applicant. And then we compute the occurrences for each job advert, how many applicants, how many applications did we receive. Then the next step for us is to actually construct the graph. And so in order to construct it, the graph is a heterogeneous graph. There are two types of nodes, right? The first type of node is the job advert, and the second type of node is the applicant. And so here to construct the graph, we just go through the dictionary that we built for the job advert and the occurrences, like how many applications did we receive. And for that, we use that to actually extract the information. So when we're building our graph, we make sure that for each job, also our heterogeneous graph will have small clusters, kind of, and each cluster will take one job advert, and then all the connected nodes will be the applicants, right? And that's what we're doing in the for loop. And in some cases, because we haven't received, because you don't expect all the job adverts to receive the same type of application, the same number of applications, yet when you're constructing the graph at the end of the day, in order for you to pass that graph to the graph neural network, you need to have uniformity in terms of dimension. And so when you don't reach the maximum number of applications, and that's why we compute the maximum number of applications. And if you don't reach, you just fill it. And I think that's what's happening in this this line here. What we simply do is just augment with empty edges, right? So that we make sure that all the graphs have the same size. And then here was simply, so this was just a description of the build graph function. This is actually where we are constructing the graph. So we simply pass the sorted occurrences and then all the data that we've loaded, the applicants and the embeddings, both the applicant embeddings and the advert embeddings. And once we construct our graph, then we split the graph that like you would do typically when you're training a model, right? Your training and test data, right? So our training graphs and test graph, we split them 80%, 20%. And then we use data loader to then map the data loader to actually create the data set for training, the training load and then the testing load. Now, the model itself. So for the model itself, I take you back a few steps back. This is our model, right? So now we have to, our model actually includes the graph neural network and the intermediate layer where we harmonize everything before we pass it to the transformer. So this is actually the model that we're implementing here. So we are adopting the typical transformer implementation where we have 6 layers for our encoder and 6 layers for our decoder. And then we build a sequence to sequence by combining the encoder and the decoder. So the next step is actually the whole model, as I presented graphically, is represented in the structure where we have a data structure that actually captures the graph neural network, the intermediate interface, and the transformer. And then we just write a function to instantiate such a model. I should say that because we use sometimes, so when you're generating the graph neural network, you have to decide whether you're using a single convolutional layer or a combination of convolutional layers. And so if you're using a combination of convolutional layers at this stage, you should, instead of just passing that convolutional layer, you should use a chain of them and indicate how many convolutional layers are actually being combined in this graph neural network. So in this instance, we're combining the GAT convolutional layer and the RGGC convolutional layer together in our graph neural network. And then here we simply instantiate the model with all the parameters and go ahead and then we train the model. Here, I should also point out that typically when you build a recommender system, one expects you to create a classifier, right? But here we're doing a regression because what we want is actually for the transformer to learn how to score, how to actually generate a score for the I should say, the adequacy or how much a candidate or an applicant is suitable for a job application, right? So here we focus more, our model actually produces a regression. And then we train the model based on that. So we simply train the model, right? And then once we, so we use once with the function, the train model function that is defined, the next step for us is to then train the model on all the workers that have been allocated for our job. And we simply make sure that there's a synchronization and the HPC takes care of through the call to the distributed and sync. The HPC makes sure that the different workers are synchronized across the different compute nodes. So we don't have to worry about that. One important point is that I haven't used a package like MPI at all, but it is possible that you consider MPI or even Dagger, that you use MPI through Dagger or direct MPI in your implementation, particularly for the data preprocessing, right? So if your data preprocessing is so large that you can handle it on a single node, that what you can do, or you don't want to use distributed for the second part where I showed some distributed calls. If you don't want to use distributed to do it, then you could actually call use MPI to do so. And here I'm just highlighting the two essential collective communication calls that you could consider, which is all gather and all reduce. And this is just one example where we take all the job adverts. Imagine that you have all your job adverts in a folder, and then you want all the different nodes that are participating in the pre-processing to just focus on pre-processing a portion of the file. So what you could do is on rank 0, make sure that you get all the files, the name of the folder, and then you construct the files. And what I'm doing in assign to rank is actually assigning specific files to a specific rank, right? So I will take for each rank, I'll jump because I have the size determines how many processes I have, right, in the communication world. And so when I jump by size, I can then make sure that if I, for example, I have 25 and I have 4 components, every 4 steps, I'll just keep skipping, right? And then I can go back to the process assign adverts is very similar to what I did in the previous case, only that this is a subset of the files, and this has been assigned to a particular rank. So once it's done, right, the rank will now have to communicate. Once they finish the processing, they got the small extracted adverts, and now you have to aggregate. So what I want to do is not to gather everything on the rank 0, but make sure that all the components receive a copy from all others, right? So I'll rather do an all gather, and in this case, I'm sharing the keys and the values of the rank adverts that has been constructed. So it is the adverts that have been extracted from the different ranks, the different processes, and they're all aggregated and combined on every nodes that are participating in the MPI job. So I think it's time for me to wrap up. So in summary, what I discussed here is the implementation, I should say, of a recommender system that focuses on candidate pre-selection in a recruitment process. It is a hybrid architecture where we combine graph neural networks and transformers, and in between we have a neural network that serves as an interface to flatten everything. Our implementation focuses on a parallel or HPC environment where we take care of the data pre-processing using the distributed package. And also, I just showed you a way of doing it with MPI. And we also train the model in the distributed environment. Thank you very much.